My name is Cassidy. I am the community librarian with the Edmonton Public Library. I am very, very excited to be partnering with Future Energy Systems to offer this speaker series today. We are really excited to be doing a couple different online talks, and we had done, I think, only 2 in-person ones when we had to close due to COVID, so I'm very happy to be moving online. I'm not going to chat too much because you're not here to talk to me or hear from me, but I do want to do a little bit of housekeeping before we get started. So most of you already have turned your audio and video off. That's perfect. Just to help with the quality of the video while the presentation is happening, if you can just keep it off, that's great. There will be times that if you want to ask a question, there'll be time to do that. We are going to be recording today's talk though, so if you want to ask a question and you're not comfortable being recorded or having your voice recorded, you can also use the chat box to ask the question. If you haven't used Zoom before, there's a little chat box at the bottom of your screen just left of center, and you can type in there any questions you might have, and either myself or you might see Valerie from Future Energy Systems on your screen waving right now. We will relay them onward. But you are welcome to pop on video or audio and ask your question yourself as well. Just note that it will be in our final recording. I think that's everything that I have to talk about. So I'm going to pass it over to Valerie, and I'll keep admitting people as we go along.
Hi, everyone. I'm Valerie Miller, and I'm the Outreach Coordinator for Future Energy Systems. Future Energy Systems was launched in 2016 with a $75 million grant from the Government of Canada's Canada First Research Excellence Fund to help fund Canada's transition to a low-carbon energy economy. We focus on multidisciplinary research that develops the energy technologies of the near future, integrates them into today's infrastructure, and examines possible consequences for our society, economy, and environment. We also contribute to the development of solutions for challenges presented by the current energy system. At present, we have 104 research projects, 655 graduate students, postdocs, and highly qualified personnel, and 139 researchers. So we're pretty big right now. The University of Alberta would like to acknowledge that we're located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. And we want to welcome you all here tonight. We also wish to remind that the current and future viewers that the opinions expressed by the speaker are not necessarily those of the Edmonton Public Library, Future Energy Systems, or University of Alberta. And now I would like to invite our speaker to pop on. Dr. Arvind Rajendran is going to be talking about carbon capture and climate change. So welcome.
Well, thank you so much, Valerie. Good evening, good morning to people wherever they're joining from. We are meeting under unusual circumstances. So first, let me quickly say that I hope all of you, your families are doing well, and thank you for deciding to spend the next hour or so with us here. So my name is Arvind Rajendran. I'm a professor of chemical engineering at the University of Alberta. For those of you who are joining from beyond Edmonton, beyond Alberta, University of Alberta is one of the leading public universities around the world, and I'm really proud to be a part of it. And I'm even more happy that this is organized through the Edmonton Public Library. For those of you who don't live in Edmonton, the Edmonton Public Library is one of the best public libraries that I've seen around the world, and a lot of us benefit from it. So first, let me thank all of them. So I should also thank all our sponsors, all our funders. Most of them are Canadian public institutions. In particular, I should thank the Canadian and the Albertan taxpayers, because it is their money that allows us to dabble in science and to train our students. And last but not least, I should also thank all our students here. This was a picture that we took before the COVID came in. This was almost last year. And we even photoshopped Gwen Liske here, who's probably in the audience. So before we go through this is a bit of a controversial topic, so I should make some disclosures. So our research work on CO2 capture is entirely funded by Canadian Albertan, and we also receive US Department of Energy funds for some of the work that we have done and currently doing. We are discussing with energy companies for potential joint projects on CO2 capture. We have not come to a conclusion yet, but I felt that it is important that I mentioned that. I don't do any consulting work, or I have no financial interests, including stocks or shares that benefit from this technology. So I hope that I can provide an unbiased view this evening. So I will also start my talk with a basis that human-induced climate change is real and CO2 plays a key role. If we don't agree on that, then the entire talk might not completely make 100% sense, but if you still follow that but are looking for a big engineering challenge, you can also look at this as an engineering challenge by itself. And also, I'm not a climate scientist, so I might be very poor in refuting some of the discussions that could center around that. But from my perspective, I think there is enough evidence to show that CO2 and greenhouse gas emissions are one of the most important contributors to human-induced climate change. So the agenda for today's talk would be as follows. So I will talk about CO2 capture for most of my talk. And the second half, or the second, I would say, the 1/3 of the talk would talk about our research at the University of Alberta, where we are looking at specific processes that have the potential to reduce the cost of CO2 capture. And my target really here is the general audience. So kindly excuse me if I make some vague and very broad generalizations. So the intent is to communicate what this technology is and what is the status of it, instead of delving deep into the nitty-gritty details about the numbers. But I hope to provide you with a good ballpark information of the numbers that could help you to understand this technology. So let's go in. So this is the first part of my talk, which is on CO2 capture. So when we start looking at this whole problem, let's start looking at the annual greenhouse gas balance. And what I'm going to show here are numbers that are contributed by human activities. So I'm not looking at the natural activities, which are much bigger in scale. But if you look at the most important human activities, they can be categorized broadly in these terms. And as you can see here, energy, industry, and transportation are some of the biggest hitters in terms of contributions. And I will keep referring to gigatons. 1 gigaton is 1 trillion kilogram. So you can imagine how big these numbers are. So if you look at the positive contributions that are added to the atmosphere, they're about 38 gigatons of CO2 equivalent. So we call it equivalent also because there are other gases such as methane that are contributed, and we usually calculate their emissions in terms of CO2 equivalents. So it gives a broad unit for us to think about these emissions. There are also activities that take the CO2 from the atmosphere and put it in the ground, and that broadly classifies or goes into about 21 gigatons. So I teach chemical engineering at the university, and one of the first courses that we do in chemical engineering is talk about conservation of mass. And the most basic equation that we learn is that accumulation is simply equal to in minus out. So you're adding about 38 gigatons to the atmosphere. You're removing about 21 gigatons of CO2 every year. That gives you a net contribution of about 17 gigatons of CO2 to the atmosphere. So, and what happens since we keep adding CO2 to the atmosphere? The composition of CO2 has been increasing in the since the Industrial Revolution, and we know this. And currently, as of this morning, the CO2 concentration, the global average has been reported to be about 414 parts per million. When we are talking about climate change, it is also common to talk about the temperature anomaly, which is essentially the difference in the global average temperature between now and the pre-industrial era. And that happens to be around 1 degree Celsius. So in 2015, most countries around the world got together and signed the Paris Agreement. And in short, what this agreement does is that it provides a motivation and a commitment to make efforts to keep the global temperature rise well below 2 degrees, which means so we have only 1 more degree really to play with, and to pursue efforts to limit the temperature beyond 1.5. So we are going to say we certainly have to keep it below 2, but we'll make every effort to keep it below 1.5. So since this talk is primarily addressed to the Canadian audience, Canada also ratified the Paris Agreement in 2016, and it put forward a plan where it will try all it can to reduce the emissions by at least 80% in 2050 compared to the 2005 levels. So there is a strong commitment from Canada to work towards meeting the goals of the Paris Agreement. So if you want to look at numbers, these numbers are provided to put things in perspective a little bit. So I picked up the greenhouse gas emissions for different constituents. So here is for the world, for Canada, and for Alberta. I've also listed the per capita greenhouse gas emissions. These are in tons CO2 equivalent per person per year. So if we consider ourselves to be a citizen of the world, we contribute about 4.8 tons per year. If we think of ourselves as citizens of Canada, we contribute about 20 tons CO2 per person per year. And if you're from Alberta, it is all the way up to about 61. And this is very, the numbers really jump out, but also if you put this in perspective to where the big industries are. So Alberta is, I would say, a very key province in Canada. It is the industrial powerhouse of Canada in a way, and the industries located in Canada are energy intensive. So that explains the high greenhouse gas emissions. But needless to say, by contributing this, Canada also contributes to the growth of Canada. So we also have to put these two things together when we are judging these contributions. But nevertheless, I think we have an imperative to reduce these emissions far below what it is currently. So if you look at the greenhouse gas emissions, one of the ways would be to ask, okay, how can we mitigate greenhouse gas emissions? And we can think of several ways in which we could do this. And here I wish to show a very simple schematic of what are the different ways in which we can do this. So for instance, we have a chemical or a power plant, and we use fossil fuels. This produces CO2, and then the CO2 is emitted into the atmosphere. So we could now aim different parts of this chain and ask, okay, how can we reduce emissions? And I'm going to list a few ways in which this can be done, starting from the source of power itself, of energy itself in this case. One obvious way, and this is something that people around the world are doing, is to do a fuel switch. Which is essentially, if you think of coal, the simplest way to think of coal is that for every atom of carbon, you have 1 atom of hydrogen. So you can think of coal being simplified as a molecule that just contains 1 carbon and 1 hydrogen. Of course, it's not balanced from your chemistry perspective, but on an average, that is what it is. So if you look at methane, on the other hand, which is natural gas, you have 4 atoms of hydrogen for every atom of carbon. So when you burn methane as compared to coal, the specific emissions for every joule of energy that you produce is much lower in terms of methane as compared to coal. So one of the ways in which we could transition from an energy or a CO2 intensive power generation to something that is much better is to consider fuel switches. And this is something that is being actively pursued around the world. And I was reading just a couple of days ago that UK, which was a big, which was dependent on a lot of coal, has dropped its coal consumption so much that in the last month or last 2 months, I believe they had about 20 straight days where they did not consume a gram of coal to produce power. So you could see the amount of commitment that many countries have in terms of moving away from coal into something much more cleaner. And this might also be an incentive, considering the low natural gas prices that are available at this moment. Of course, the other big aspect that has to be considered is to look at renewables. So Canada is heavy on hydro, and by increasing hydro is one of the ways in which Canada has, over the last few years, have reduced the per capita CO2 emissions, and that is an area where I believe there would be a lot more action. Solar is something that is coming up. Maybe in Canada, the potentials are much lower than in many other places, but solar seems to be unavoidable in the near future. The other way is we could target what happens within the power or the chemical plant. And here, one of the low-hanging fruits, as many people consider, is to improve the efficiencies of this plant. So which means that you make your processes more efficient so that you have to burn a lesser amount of fuel, fossil fuels in this case, in order to do the same thing or even more. The other option is also to come up with new ways of generating power. But very often this is a place where you're also limited by thermodynamics. So the scope for improvement is there, but I would say there is a lot more scope on other places. The other place where you can, of course, affect is to look at what comes out. Here we have CO2. And one of the ways of reducing CO2 emissions, if you're targeting at this node of the chain, is to use carbon capture, utilization, and storage. And this would be the talk, this would be the focus of my talk for today. Of course, finally, once the CO2 has been emitted into the atmosphere, there are also technologies which are called as negative emission technologies, where the idea is to remove CO2 from the atmosphere and to store it under the ground. So we would probably also spend some time looking at these technologies today. So if you look at all of these different mitigation pathways, the Intergovernmental Panel for Climate Change, in short IPCC, came up with the fifth assessment report recently. And they looked at multivariate scenarios by using different modeling tools. And they said, okay, if we now consider different energy mixes that could be available in the near future, and if we want to meet the Paris Agreement, and the goal would be to go to a net zero emission by about 2050. So, and with that goal in mind, so if you look at the plot on the right-hand side, so you look at this, so here is where we are currently at around 38 to 40 gigatons of CO2 emission. And if you look at how people expect that the emission levels would evolve as a function of time, could be observed in the following manner. So if you look at the gross emissions, you're likely to go through this path here, along this path. And here is where the zero line is. So keep an eye on the zero line here. If the gross emissions are expected to go along this way, and if the goal is to reach net zero by 2050, people also anticipate that sometime around in about 2030 or so, we should start looking at negative emission technologies, which are shown here in the yellow, which is essentially BECCS, and I'll talk to you about this in a moment. But what you also see are options to reduce the emissions by using carbon capture and storage, which are shown here in this orange wedge. So it is anticipated that carbon capture and storage would start kicking in much in the very near future. And it's going to act like a transition technology until we reach a mastery over other technologies that will have lower emissions. But the important point to note is that even after doing all that we can, you see that there are some emissions right here. So this is where the zero line is. But you see that even after converting everything, there is certainly a portion of emissions that cannot be avoided. So these essentially come from chemicals, from aviation, and so on. So which means that in the long future, we cannot ideally go to a completely zero emission future. But if we want to offset this, we have to come up with other technologies, which are called as negative emission technologies. So where we actively pursue pathways to take the CO2 out of the atmosphere and then store it somewhere safe. So if you look at this technology, this forecast or the mitigation pathways, one of the things that pumps up is immediately that there is no silver bullet technology. We are going to most likely achieve these targets, if we achieve these targets, by considering a mix of technologies, which could involve any or even more technologies as what I showed you in the previous slide. But you also start seeing that even in the near future and in the long-term future, carbon capture and storage is seen as a potential option for reducing emissions and also to target, I would say, negative emissions in the future. So what is this concept of carbon capture and storage? So let me explain this with a little cartoon. If you look at the system, so we have the atmosphere and we have the litho and the hydrosphere. So how did we get these fossil fuels? So the trees and the other organisms took CO2 from the atmosphere and they went into the ground. And after thousands or millions of years, we start forming fossil fuels. They could be either coal, oil, or gas. So until now, I would say, our predominant source of energy has been fossil fuels. And what we have done is we have found ways of extracting it through advanced technology in some cases. And once we produce this, these are used in many applications. So and these are the sources. When I call them sources, these are sources of emissions. And we identify, or we broadly classify these into two different classes. One being point sources, which are really fixed, where you have very large quantities of emissions in a concentrated geographical location. And then you have the distributed sources like transportation, for instance, where things move while emitting greenhouse gases. So, and of course, in the previous slides, we have clearly shown that the emissions that come out of point sources are much larger compared to what we have from distributed sources. And these emissions eventually end up in the atmosphere, and these are the ones that we need to now try and avoid. So what are the ways in which we could do it? And specifically, this is where carbon capture comes in. And the idea here is that we take all of these point sources, and if not all, as much as we can, the point sources, and we capture the CO2. What it means by capture is these tend to be fairly dilute sources in CO2, which means the concentration of CO2 is not very high. And I will show you examples of what these ranges could be in a subsequent slide. And then we concentrate CO2, which means we are doing a separation between CO2 and the other gases that are present in the mixture that comes out here. And once we concentrate CO2, we transport, we have to transport it. But before that, it is very important to highlight that in one of the first aspects that we would teach in thermodynamics is that when you mix two gases, you don't spend energy because that is what is the preferred state. But when you now have to separate anything, then you have to put in energy. And there is a difference between the thermodynamic energy that is required and the actual energy that is consumed in these processes. And what we have seen is typically in very mature separation processes, the actual energy that is used is somewhere around 2 to 3 times the thermodynamic minimum. But the important point being that this requires energy, and this energy should either be supplied from a renewable source, or the energy that is required to do the capture would create additional emissions, because if you get it from fossil fuel-based plants, you will create additional emissions, and you have to compensate for that by capturing all of them. So this energy is something which is critical, and the point being that capturing is not free. So there is an energy penalty that is associated with capture. So once you capture, you have concentrated the CO2, this has to be transported to a location where it can either be used or it can be stored safely. There are different ways, and I will show you an example of a pipeline. And being in Alberta, seeing pipelines should not be uncommon. So pipeline transport is one of the preferred modes. But people are also now talking about shipping CO2 from one location to the other. For example, if I look at some of the blueprints that come out of Europe, they're planning to have centers where different ships that bring in CO2 can come in and eventually store CO2. So once you're transported, you go to the last stage, which is essentially either utilization or storage. So in the utilization, the idea is, and this is a common question that comes up very often, CO2 is available, why not we convert it to a different product? And I will address that in a moment. But one of the aspects to consider here is that if you have to utilize CO2, and for instance, converting CO2 to methanol is a very commonly discussed utilization strategy, we would need hydrogen, which should ideally come again from a renewable source. We might need minerals in order to convert it to, for instance, a carbonate. And once we take this, and with the addition of energy, we might be able to produce products. So this is what we would typically call as the utilization pathway. The utilization discussion has become more prevalent in the last few years, I would say. The other option is, of course, to store the CO2. What we do here, we take the CO2 that comes from here, compress it, and the idea would be to pump it under the ground, preferentially, and to store it either in geological formations. For example, used wells are one of the classical locations where CO2 can be pumped into. People have tried looking at storing it under the ocean. The Sleipner project in Norway is a classic example of that. And the other option is also to mineralize it. So which means that you take rocks and you combine it with CO2 in order to convert it to carbonates where they are not released for a very long period of time. The other option, which is practiced, is what is called as enhanced oil recovery or enhanced coal bed methane. And the idea here is that we take part of the CO2 and we use that to push some of the oil that could be in a well that has been deemed to be fairly producing very poorly, or even to store it in coal seams, which are of very low quality. And the idea here is that by doing so, we will push out some amount of CO2 or gas, which can then be taken into this chain. There are some calculations which also show that the enhanced oil recovery and enhanced coal bed methane processes can be net CO2 negative. So which means that we, depending on the type of formations we have, we might end up storing a net amount of CO2 compared to the amount of CO2 that will be produced because of taking the oil or the methane out. So this is the summary of how a CCUS chain might look like. So now if you look at the costs of the different nodes in this chain, it becomes clear that this is not a very cheap process. For instance, the capture can vary anywhere between $15 to $75, and these numbers have not been very clear in the literature, and I will talk to you about this in a moment. Transportation seems to be the most cheapest, about $1 to $8, depending on how it is done. And the storage can be as low as, people have calculated it to be as low as $1 or so, because in some cases there is an economic incentive because you're going to be producing additional fuel, and that could help to offset some of the costs. So if you look at this chain here, it becomes fairly clear that the capture step is where the most expense resides. So if we want to make this process any cheaper, we need to focus on being able to capture. And if you also look at this, this becomes a prerequisite for doing anything else. And why do we need to concentrate? For very simple reasons. Remember, if I don't have a very high purity of CO2, I'll be spending a lot more energy in transporting stuff that I don't need to sequester. Okay, so that gives us a picture of how the costs are for the different components. So when we talk about CCS, it is also important to realize that we are not talking about just one source or one stream of CO2, and there are, in fact, a variety of sources that are possible. So what I've plotted here is the composition of CO2. When I say 5% when you have 100 molecules of the gas mixture, 5 molecules are CO2. And I've plotted it all the way up to about 20+%. And if you look at the concentration of CO2 in the atmosphere, it is about 0.04%. So this is where the atmospheric concentration is. On this axis here, I've plotted the annual CO2 emissions from each of these sources in million tons of CO2 per year. What does this mean? From a very simplistic perspective, if you're trying to concentrate CO2 from a particular stream, the more dilute the stream is, which means the more closer you are to this end of the plot, it becomes very difficult. The simplest analogy to think about is picking a needle from a haystack. You have a lot of hay and you're looking at very, very small concentrations. So indeed, you will be spending a lot more energy. And the other point to consider is also, in order to pick that one needle, it is very likely that you have to process the entire amount of hay, which means that you also require very huge equipment in order to deal with the throughput of the entire gas. So which means the more closer you are to the left-hand side, the more difficult is the separation. And the more closer you are to the right-hand side, I'm going to call it less difficult. Let me not call it easy, because it is not easy. I'll call it a less difficult at this end. On the y-axis, if you are further up, it means that you have a higher mitigation impact, so which means that you can make a big dent in terms of your emission reduction. And if you are towards here, it means it is low. So if you look at the different big hitters in this case, this is how it turns out to be. For example, coal tends to be around 10 to 15%, and it contributes to about 8,000 million tons of CO2 per year. Natural gas, for instance, simply because, as if you remember, you have 4 atoms of hydrogen for every atom of CO2. So which means your CO2 composition that comes out of a natural gas power plant is much more dilute in terms of CO2. And then fuel oil is somewhere in between that of natural gas and coal. And of course, there is a wide range of these numbers, but I would like you to get an idea of where they reside. And on the other hand, you also see industry. So if you look at this, the red squares, I refer to the power generation systems, whereas the green ones are chemicals or industry. As you can see here, cement, on one hand, it has a big CO2 emission amount, about 1,000 million tons per year. But it also has the advantage of having a CO2 stream that is far more concentrated than any of these. So if you look at this plot, you can also see that these regions, which are primarily available there for generating power, they also have the potential to be replaced, for instance, by renewable energy sources. Whereas these aspects here, the green ones here, necessarily relate to industry, which are unlikely to be affected by power generation, but also provide us an opportunity to start looking at a CO2 capture. The other aspect to consider is that in many cases, it's also possible that you have to remove the CO2 because you have to get your product in a pure quantity. So these allow us to consider implementing a CCS. So there are also some approximate numbers, and I provide you some approximate numbers from one of the CCS reports. And as you can see here, in all of these cases, it is upwards of about 55 US dollars per ton of CO2 captured. So the main message from this slide is that when we think of CO2 capture, we should not only think of a CO2 capture from the power industry or from just one source. There are a variety of sources available where one could consider implementing this technology. So if that is the case, are there CCS projects around the world? Yes, there are plenty. And this is a map that shows the different projects at different stages. If you're interested, I would ask you to look at this map at the Scottish CO2 Capture and Storage Organization, and they give the status of different projects. And as you can see here, Europe has been looking at it very intently. North America, specifically the US and Canada, and I will show you how Canada is a leader in this technology in a slide or two. And China and Japan have been very serious about it. Australia is also getting very serious also because of the increased natural gas importance in Australia. So I've been telling you that Alberta is a leader, or specifically I would say Western Canada is a leader in terms of very large scale CCS demonstrations. And it is interesting that two of them are very close to where I'm located, which is in Edmonton. The first one being the Shell Quest project, which is in Scotford. It's about an hour drive from here in Edmonton up north. And this project has been up since 2015, a fairly successful project. And it's designed to capture 1 million tons of CO2 from a year. This is located in an upgrader where oil from up north comes down to the Scotford refinery, and they require a hydrogen, and the CO2 is removed from hydrogen. The total project cost for the CCS portion has been reported to be in the order of about $1.3 billion. And I believe Shell did receive support from the governments. So the captured CO2 in this case is pumped 60 kilometers up north from Scotford, and it's injected in a well, which is about 2 kilometers deep. And so far, I think this was just a couple of weeks ago that Shell reported that so far since 2015, it has sequestered 5 million tons of CO2. The other one is the Sturgeon refinery and the Alberta Carbon Trunk Line. So these are very new additions. And the Sturgeon refinery is as I understand, is a refinery that has been built in Canada after a very, very long time. And when they built it, they had a gasifier to which they added a carbon capture system. And that feeds into what is called as the Alberta Carbon Trunk Line, which takes the CO2 from the Sturgeon refinery and through a 240 kilometer long pipeline. It is being injected in a place called Clive here in Alberta, and it is used for enhanced oil recovery. So the plan is that the Alberta Carbon Trunk Line will also facilitate the addition of other CO2 capture facilities within Alberta and eventually use it for enhanced oil recovery. So this project was just commissioned very recently. And as I understand, this is designed to capture about 1.7 million tons of CO2 per year. The other famous project is the Boundary Dam project in Estevan, which is very close to the US border in Saskatchewan. And this is an interesting project because this is a coal plant, as you can see here in this picture. Let me see if I can zoom this. So this is a coal plant. I believe it is about 550 megawatts. And they capture the CO2 from 1/5 of it. And this is the CO2 capture unit that you see here. This big unit is where the CO2 is concentrated. And this is one of the first large-scale demonstrations of what is called as a post-combustion capture, which means it captures the CO2 that comes out of a coal plant where you use air as the oxidizing agent. It is designed to capture about 1 million tons of CO2 per year. But in practice, I believe it is captured on an average of about 0.6 million tons of CO2 per year, specifically in the last year. And I believe in the last few months, it has been up about 90+% of that time. This was again a project that was built very heavily at around $1.4 billion. And in this case, the CO2 is captured, which is captured here, is pumped about 60 odd kilometers, and it's used for enhanced oil recovery. So as per the website from Saskatchewan, from SaskPower, they have stored up to about 3.5 million tons of CO2 from this particular project. So the question that we often get is the difference between storage and utilization. So we saw what utilization can do. The idea is essentially to take CO2 and to convert it to anything useful. It's a buzzword because suddenly we have a new source and it's being wasted. Of course, there's an urge to start thinking how we can utilize it, and I think it's a very important aspect to think about, because now we can think of CO2 as being one of the primary sources of carbon for anything down the line. But it is worth recollecting that so far the largest consumer for CO2 is enhanced oil recovery, about 70 million tons a year. And when I say this largest consumer, this is one of the ways in which CO2 is eventually sequestered. So for instance, you would often get questions saying, okay, why not we convert it to, let's say, a urea or add it in soft drinks? But we have to keep in mind that these forms will eventually lead to the CO2 will just leave, and then it is not sequestered for long enough periods of time. But the real aspects that come out when people start doing life cycle studies is that, one, is that there is no sufficient market for anything at the scale of what we produce. For instance, if you look at sulfuric acid, which is the largest produced commodity chemical, it has a market of about 230 million tons. Compare this to CO2, which is much, much more. So even if we want to make a big dent in the CO2 that is being released, as I mentioned earlier, we also require other components that have to come in, either minerals or hydrogen. So when you now think of hydrogen, we also have to realize that the hydrogen that has to be used in any of these processes should exclusively come from a non-fossil fuel source, or in other words, green hydrogen. One of the ways in which people are trying to get green hydrogen is by splitting water, by using electricity, which comes from a renewable source. But again, we do have to keep in mind that the electricity has to be also from a renewable source. Otherwise, this chain might not take us too far. The final aspect to keep in mind when we think of utilization is we also have to look at the entire life cycle of a CO2 molecule if it goes into any of these particular forms. We also want to make sure that the CO2 is not released immediately, but it has the potential to stay at a particular location on the ground for a long enough period of time. So whenever we are considering discussions around utilization, these points become very critical. Storage, on the other hand, storage places plenty, and that is what many surveys tell us. And with proper choice of site and monitoring, storage can be potentially safe. This is what has been done in the case of Shell Quest project, as I've just discussed. But on the other hand, there are also risks that are associated with storage, for example, leaks, induced seismicity. So these are aspects that really have to be kept in mind when people are looking at CCS projects. The other critical aspect happens to be the availability of a storage site near a point source. And this, I would say Alberta is an exception in this case, because we have adequate storage sites and point sources right next to each other, but this is not the case all through the world. So these factors could play for or against storage and utilization. So I'd like to now switch gears and move to what we called as negative emissions. So the negative emissions are the ones that are shown here. And here, the idea is we actively start working towards technologies where we can remove the CO2 from the atmosphere and push it under the ground. And many mitigation pathways considered by the IPCC, by different countries, seem to put a huge weight on the availability of negative emission technologies. So in addition to that, why should we start thinking about negative emission technologies is one of the aspects seems to be that the negative emission technologies allow us to de-link the point source and the storage constraints. So for instance, the hypothetical idea is that you could now remove CO2 anywhere on Earth, preferentially next to a storage site, and hence we could, of course, de-link this problem. The other aspect, if you remember this small portion that was shown here, these emissions come from sources such as transportation or planes, for instance. So these are difficult to be captured at the source, but the idea is that you could potentially capture them later on. These technologies are in early stages, and the expectation is that when the price of CO2 becomes high enough, these will start making sense. Of course, the key point to remember is that at this moment, capturing CO2 from a 12% source is expensive with the price of CO2 at this point. So imagine doing that with a source that has 0.04%. So that is so much more challenging. But as I will show you, there are techniques that are available to do that. So in these negative emissions, there are two aspects that are considered. The one aspect is in this chain that we have already discussed, and hopefully it is still fresh in our minds. The idea is not to rely on this multiple thousands of years of processes, but instead to grow enough biomass and use biomass as the fuel and combine it with carbon capture and storage. So this is what is called as BECCS. And this is what the IPCC reports have highlighted very much. So this yellow region that you see here is essentially the expected amount of CO2 that could be removed using a BECCS. So this is a pathway which continues to be discussed. And it appears that some of the estimates that could have been made early on might have overestimated the potential of BECCS. Because when you now calculate how much land is required in order to do this, it simply becomes too huge. The other technique is what is called as a direct air capture. And what we do here is the idea is to take the CO2 from the atmosphere and to go through any of these processes, capture, transport, and store it under the ground. So this is another technique. Of course, there are several other negative emissions techniques that I'm not discussing here, but these two couple themselves together with CCS, and that's the reason I'm bringing that into discussion. So with respect to direct air capture, there are at least two big startups, if I may call them so. One is Carbon Engineering. This is a Canadian company. They have a pilot plant in Squamish in BC. It came out of University of Calgary from the group of Professor David Keith, who's now a professor at Harvard. And they have designed essentially a three-stage process. The first process, a first stage in which the CO2 from air is removed using a hydroxide solution, then it is converted into a pellet, and then there is another loop where the pellet is heated and CO2 is being released. They calculate and claim that they could do capture from air at around $100 per ton. So this is a number that is claimed both in their website and also in a very interesting paper that came out 2 years ago. The other company that has moved on from piloting into some level of commercial operation is called Climeworks. And this is a Swiss company. And instead of using a solution in order to capture the CO2, they use a solid sorbent. And what they do here is that they pass atmospheric air. So these solid sorbents concentrate the CO2-free air comes in here. And then you take this and you apply vacuum and heat it up a little bit. And then the idea is that you can produce a CO2. So one of the advantages that they would claim for their technology is also that they could use heat, which could, for instance, come from geothermal sources. They have a pilot plant in Iceland, if I'm right, where this process takes place using geothermal heating. And they claim that currently the cost of CO2 captured is around $600. And with evolution, they expect that this would go down to 100. These numbers have been heavily discussed in the literature, And one of the primary sources for the discussion comes from a report that the American Physical Society came up with in 2011, where they estimated the cost of capture from air, direct air capture in other words, to be in and around the $600 range. So this is the status of where direct air capture is. So in my last slide, before I take some questions, I would like to talk about some barriers for CCUS. So we have the technology and it has been implemented in very large scales, but CCS has not taken up in a very big way as people expected. So there are several reasons, and I've listed a few here. One clearly is the costs are currently high compared to the cost of CO2. The price of CO2 in most jurisdictions remains at or around $30 to $50 per ton. In some Nordic countries, these seems to be much higher. So there is obviously an incentive to do something. For example, Norway and Sweden have much higher costs of on their CO2. So those, Switzerland as well. So those could be places where CO2 capture could become, I would say, viable, economically viable. The other aspect that we see also within the community has been that the variability in the cost estimates are quite large. So it's very difficult to narrow down on the costs of what is possible. And part of it also comes from the fact that many of these plants are first of a kind plants, and we don't have enough experience building such plants. So there is a lot of uncertainty that surrounds the cost. The other aspect is also several large-scale CCS projects. They have had either cost overruns or they have had much lower uptimes, online times as compared to what they were designed for. The classic examples in this case being the Boundary Dam project and also the Petronova project in the US, which had operational challenges. But what the Boundary Dam has done over the period of time seems to be that they have learned and from early design issues, and now they are able to run it up to about 90+% online time. Storage is an issue which makes it difficult to implement CCS in many places. I would say Alberta is a unique exception in this case. And the next point being the market. With the current economic structures, with the prices, there is really no market for a CCS. Specifically for utilization, the costs involved seem to be high. Finally, the public perception is that CCUS is a way to have companies and countries to continue using fossil fuels while not doing enough for the environment. So that is one of the clear perceptions that seems to be out there. And finally, there is also a concern over safe storage. So these are some of the barriers that exist for the implementation of CCUS. I will pause here to take a couple of questions, and then I will take maybe about 5 or 10 minutes to talk about the work that we are doing here.
All right, if there's anyone with any questions, you can pop it in the chat box or you can go live. One of the questions that we got was, how can we reduce the cost of carbon capture to make it more economically viable?
So one clearly is looking at other technologies, and I'm going to talk about it in a moment. The second aspect is we also know from the past that as we get technologies moving from one end to the other, we learn more about how to do it, and once we know how to do it, we do it in a better way. So these are different ways in which you can consider lowering the costs.
A question we got from the audience: can you tell me more about the adsorbent materials to capture carbon dioxide?
Yeah, I'm going to talk about it in a moment. Yeah.
All right, it's coming up soon. Another question we got is, can we scale carbon capture technologies to attach to houses and cars rather than just large industrial processes?
In principle, yes, but in practice, I'm not sure if that is going to be logistically possible. So, and that is why I think many of these conversations around capturing from what are called these as mobile sources has not taken up at all. Because now once I've captured my CO2 in my car, there are two things I do. One is I'm adding mass to my car as I'm traveling, because I'm taking the oxygen from the atmosphere and storing it in my car in one way. And the other one is, okay, once I've captured it, what do I do with that, right? So, so those logistics seem to not be in favor of that. And the easier locations to focus attention would be, of course, on point sources, where you have these huge amounts, and you also work on the economies of scale, right? So when you build larger and larger chemical plants, we know that the costs go down. They are not linear as compared to the size. So these aspects do not favor capture from mobile sources.
The next question, are examples of storage points in Alberta areas which have already been mined for fossil fuels?
Yeah, it appears so. For instance, the storage from the Alberta Carbon Trunk Line seems to be in wells that have been used before, yes.
Okay, how long do carbon capture materials last? When they are discarded, are they toxic, or are there any considerations that need to be considered?
Yeah, I'm going to talk about that in just a moment as well, because I think they are very important points, especially CO2 being, CO2 by itself is not toxic, but it is very corrosive. So you start having other effects in these plants where the material starts to corrode, and sometimes the liquid that you're using to absorb CO2 can also break down, and some of it might escape. And there are very, very small, I would say, risks of them being toxic, but there are issues of them leaking, but not major ones in my mind.
Okay. Would storing carbon dioxide in oceans lead to increases in acidity of the oceans, affecting marine ecology?
So from what I understand, for instance, the Sleipner project looks at aquifers which are nicely protected by cap rocks, and it is very important to choose sites in such a way that those leaks can be mitigated. The other thing that companies or governmental organizations that do injections is also they commit to a long-term monitoring where they do seismic tests in order to see where the CO2 is moving. So these have so far prevented CO2 from leaking from marine environments.
What are the environmental impacts due to storage?
At this point, I'm not sure about the environmental impacts. Of course, there is the risk of leaks. And if it leaks, then there's always a concern that it could go into the water streams and all of that. But beyond that, I'm so far I'm not able to see a much bigger environmental issue around that.
What do you think of the idea of combined carbon dioxide capture and utilization into chemicals and fuel?
It's a good question, and that is something that I addressed in the utilization area. We do this all the time. For example, in the urea process, for example, you first manufacture ammonia, and CO2 is a byproduct of that, and then you react ammonia with CO2 in order to make urea. But what happens is when you use urea, the CO2 eventually escapes. So the idea has been CO2 could be converted into methanol. And the challenges there are the catalysts that are required to make them efficient are still in very early stages. And the second aspect is they again require energy because you're starting from CO2, which is a fairly stable molecule, and you have to now add energy. And as I mentioned, that energy should be from a non-fossil fuel source. So that becomes very critical.
Is it possible to send them into the atmosphere?
The
stored carbon dioxide into the atmosphere rather than storing on Earth, I think is what the question is asking.
Okay, because isn't that what we're trying not to do?
Oh, beyond the atmosphere into space.
Oh, It's a good point. I don't know how much energy that is going to take. Maybe we should ask Elon Musk.
What is the outlook feasibility of using supercritical fluids as a facilitator for carbon capture?
Yeah, supercritical fluids that has been an area where we have studied. The challenge with supercritical fluids, for example, CO2, I'll answer it in two ways. One, because the most common supercritical fluid is CO2, and it is used for extracting coffee, for example. That's one of the most famous applications. It is heavily used in hemp extraction in the last few years. But in that application, CO2 is eventually released. So that is one aspect that one has to keep in mind. It is not positively sequestered. The other perspective, I'm not sure which supercritical the person has in mind, but I'm also wondering how it could facilitate CCS. So maybe if they can explain that, I'll be able to delve a little deeper.
Okay, if that was your question, please add more information. Amines are quite commonly used for carbon dioxide capture in the upstream industry. Can we extend their use to carbon capture? How about the cost comparison?
It's a good question. In fact, in Boundary Dam, it is an amine that is used for this large-scale capture. And we have been using amines for 50 to 60 years in hydrogen plants or methanol or ammonia plants. Some of the issues that I've heard from people who actually use that is the flue gas that comes out of many of these plants is not as clean as what we had in the upstream plants. And there is a lot of oxygen, and oxygen essentially contaminates. So for instance, you add more oxygen for the combustion to take place in your boiler, and essentially that leads to a decomposition in the traditional amines. So people have, for example, CanSol, which was, I believe, a solvent that was developed in Canada, is an amine-based solvent that is used for CO2 capture.
Are we postponing impact of carbon dioxide by storing and buying time? Is there a limit on the amount of storage as we continue to store, if we can do it successfully?
The estimates, as far as I understand, for geological storage is in the thousands of years. So we are especially if the site is good and if you're able to do the right things, it is going to be stored for a much longer time. But again, as I would like to repeat that just because we can push it under the ground should not be a reason for us to keep producing more. I think we need to do everything that is possible to reduce our reliance on fossil fuels. But as I showed you, there are also areas in which we can not avoid them. So we should think of CCS not as a big dumping ground, but instead be strategically used to proceed towards a net zero emission world.
Okay. How significant is the barrier to mineralization of carbon dioxide?
The barriers, as I understand, are quite high. These are high temperature reactions. So except for very few places, the technology has not taken over in a significant manner. But there are, for instance, major projects in BC and some mining companies that are seriously considering using some of the tailings to be converted as carbonates.
Okay. How efficient are some of these commercial CCS facilities?
I'm trying to interpret the word efficient. So if you think in terms of efficiency of the power plant, there is certainly an impact to the power plant because you're now going to spend, so when you think of efficiency as the amount of energy that is stored in your fossil fuels, or let me put it this way. So the amount that you extract in the plant in terms of power divided by the amount of energy that is in the fossil fuels, the addition of a CCS plant always reduces the efficiency. So that is one way of looking at the efficiency. In terms of uptimes, some of these very large scale plants did have a challenging startup period. And from the reports that are available in the open, it appears that they have overcome it and they have gone to a fairly flatline mode of operation.
Last question for now.
Yeah.
Knowing on your previous slide, the carbon dioxide cost needs to be $30 to $50 a ton for CCS viability. With the carbon tax and upcoming clean fuel standard, we will approach this cost of carbon in the near term. Do you see this as a driving force forward for the use of CCS in the province and the development of associated technologies?
I think the person hit the nail on the head. What is also predicted is as time goes by, the cost of CO2 is also going to increase in terms of, because we'll become more and more desperate in order to reduce our emissions. So pricing becomes very critical in terms of CCS adoption. And the idea is also that universities, research organizations should start developing technologies at this time, so that when the correct price comes in, that's a point at which we should be in a position to implement it. In other words, as that would be one of my final conclusions, is that the current cost of CO2 or of carbon should not be the reason to keep these technologies away from being studied.
Thank you so much. So that's all the questions we have for now. There'll be time for questions again at the end, so keep putting them in the chat box and we will chat again at the end of the talk.
Yeah, and I promise that I will take about 10 minutes to do the next part. I know we are running a little late, but I hope there's something that I can show you that is interesting. This answers a lot of questions that came up earlier. So the second part, I would like to talk about adsorption processes compared to absorption, which I will show you in a moment. And this is a project that is funded by the Future Energy Systems, who is sponsoring this talk as well. And I'd like to particularly highlight a problem that we work very closely with the two other Canadian universities. One is the University of Calgary, and the other is the University of Ottawa. So here is the current process. So this is a snapshot of the process that I've taken from the Boundary Dam website. And as you can see here, here is where the coal plant is. And the flue gas, which was emitted through the stack, is now routed through a treatment. So here you remove the SOx and the NOx, the sulfur dioxides and the nitrous oxides. And then the gas goes into what is called as an absorber with a B. So what happens in the absorber is, think of this stream to contain CO2 and nitrogen. What you do is you send a liquid shown here in the orange stream, and once the liquid comes here, the CO2 is mixed in the liquid. It gets dissolved, just like how, for example, when you open a soda can, you see CO2 just bubbling out because CO2 was dissolved in water, in the case of a soda can at high pressures, is now absorbed in the so-called amine solutions. It reacts. So the stream that comes out of this purple unit contains the liquid with the CO2, and you take this into what is called as a stripper or a regenerator, and you heat the solution. And when you heat the solution, CO2 comes out in a concentrated form, it's compressed, and then it is sent for storage. What happens to the liquid? So the liquid is going through in a loop. So this is a fairly mature technology, and some of the question is asked this. It is routinely practiced in the upstream for removing CO2 from hydrogen, but implementing it in a downstream, essentially in the case of a flue gas capture, has its own constraints. One aspect that has been often cited is the degradation of the solvent, which means that we need to keep making up the solvent periodically. So that is one issue. And also the mixture of the liquid and CO2 in these environments, and especially you're also working at fairly high temperatures, tends to contribute to corrosion. So that when you consider plants of this scale, corrosion becomes a major issue, and the byproducts that could escape, for instance, through here can also be an issue later on. So as I told you, this is a process which costs anywhere between $30 to $50 a ton of CO2 capture. So there is a lot of incentive to move away from such technologies and to develop new technologies that can potentially reduce the cost of capture. And this is the place where we have been looking at an alternative technology among many others that the people around the world are considering. And we use solids. So these are called as microporous or porous solids. So these can be the form of a carbon, for example, the carbon black that you would have seen. Zeolites are another classic case. So for example, if you're in Alberta, the water is hard, And in order to soften water, very often zeolites are being used. The new kid on the block is, of course, metal organic framework. So these are very new metal organic structures that our magicians, also called chemists, are now making, where they can really tailor make these substances to either retain one of these gases or not. So these tend to have pores in the order of nanometers, very, very tiny pores. And the people have reported surface areas of these solids to be between 100 to even 10,000 meters square per gram. So which means in 1 gram of the material, you could have a space as large as a football field, provided you're a gas. Okay. So these are solids, and what has happened in the last few years is that people have found ways to tune these pores and the topologies to retain one gas over the other. For example, most materials, if you keep them at a certain pressure, will like to retain CO2 more than nitrogen, which is the other component in your flue gas. So and what happens if you can go into one of these solids, which are packed in a column? You can see that the solid, which is here, which is called the adsorbent, it is a rigid substance. And hence, because it has an attractive potential to the molecules, molecules start layering on the surface. So remember, this is a key difference between ad with a D, where molecules are sitting on the surface, and ab, in which molecules are dissolved in a liquid. So that is a key difference between ab and adsorption. So this can be utilized to perform separations. This is not new. And the idea being that if you take one of these substances, let us say you pack them in a column and you send a mixture through this, you can see how the concentration moves through the column. What I've shown here is a hypothetical CO2 and a nitrogen. And if I start this animation, you see how the profile goes. So after some time, you see that nitrogen is less attracted to the solid, so it moves further, whereas CO2 is more attracted to the solid, so it moves slower. Imagine you have, you're walking with a family member in a shopping mall, and let's say one of you doesn't like to shop and the other one likes to shop. So obviously the person who likes to shop, which means the person who likes to go into these stores or into these shops, will take a much longer time to move through the shopping mall as compared to the one who does not. So in this case, CO2 is a molecule that likes to shop, moving very slowly, whereas nitrogen is a molecule that does not like to shop, less affinity, moves faster. What it means is that if you run it long enough, you can now separate the mixture of the nitrogen and CO2. So this is the principle, the basic principle that is used in these separations. And these separations are all around us. The classic examples, of course, being oxygen concentrators that people, you might have seen people either dragging it with them or these small concentrators. These typically use zeolites in order to concentrate oxygen from the air. So these are technologies that are available. And the same principle can also be used to purify, for example, hydrogen in very, very large quantities. So you see that these technologies can scale from very small sizes to very large sizes. And this is what we are trying to research upon. So in terms of commercialization for CCS applications, I would like to highlight this company here. This is from Vancouver, also in Canada, Svante, named after Svante Arrhenius, who was the first person to calculate the extent of global warming or the extent in temperature increase because of CO2, uses a solid sorbent to do this. What they do is each of these modules is packed with a solid in a very fancy way, and they send flue gas, and CO2 gets captured here, and this bed rotates in this direction, and they use steam in order to heat up the material and kick the CO2 out of the solid, which is then collected here, which could then be compressed. And then they condition the sorbent in such a way that it can be reused. So this is a huge machine that rotates at around 1 revolution per minute. In fact, the interesting aspect is that this is claimed to contain a material that was originally developed at the University of Calgary, a form of a metal organic framework. And the claim from Svante is also that they could scale it up to capture about 3,000 tons of CO2 per day. And they are now piloting this in a cement plant in a Lafarge Holcim cement plant. So which means that there are ways in which these could be scaled up. So it is important that these are also translatable. So the grand challenge that we at the University of Alberta are working towards is, if I know, for example, the property of a material at the porous level, can I now predict what would be the potential of this material in order to be implemented in a large scale process? So for example, if I know information from a microgram or a milligram of substance, can I predict what will happen when I use hundreds or thousands of tons of that material? So you can immediately see the differences in scale as we go from where we start and where we want to be. So this is a fairly challenging problem. And here is the place where we work with the University of Calgary, who specialize in making these materials, the University of Ottawa, who have the potential to computationally calculate the properties of these materials. And we at the University of Alberta design processes so that we can now translate whatever has been developed in a very small scale to a process scale. And the goal here is we want to do this entire chain computationally. So we work with people like at the University of Ottawa who do molecular modeling. We work with process simulations, and we implement machine learning into these studies in order to come up with a techno-economic study of, if I take a specific material that has been made in the lab, can I reliably predict what would be the cost of a CO2 capture? The challenge here has been that in the last 10 years, we are now left with hundreds of thousands of materials from which we can pick a suitable solid for doing this job. And from the process side, you can configure the process in multivarious forms. And the real challenge for a scientist is now, how do we now combine each of these, which possibly many of these, in order to come up with what is the best combination of the material and a process that can do the job. So this is where our students have most of their fun. We have demonstrated some of these. For instance, we took an example of these metal organic frameworks. We started with 5,000 materials for which our colleagues at the University of Ottawa predicted their properties using techniques called as grand canonical Monte Carlo simulations. And we developed process simulation tools in order to understand what will happen if you scale up these materials. So in terms of scale, we are going all the way from molecular scale to all the way to a process in which this could be implemented in multiple ton scales. So these involve, I would say, the use of Compute Canada, where we are lucky in Canada to be to have this opportunity to use these supercomputing clusters, and we run optimizations and other models in order to come to these predictions. And what we found in this study was that compared to the thermodynamic limit, you cannot go beyond this, below this line, and compared to the state of the art liquid amine, there is a potential to find a variety of these materials that can give you lower parasitic energy compared to the state of the art amines. So of course, now remember that these materials have not been scaled up, but now this gives an idea to people as to which of these materials they need to choose. And the big advantage is, instead of them trying to go and experimentally find out from all these 5,000 materials, we can give them guidelines as to what are the few materials that are going to make sense, and they can go on the path of characterizing them, making them in large quantities, and finally translating them first into pilots and then into large scale units if everything works well. So that brings me to the last slide, where I'd like to summarize the talk today. The most important point that I would like to emphasize first as a professor of chemical engineering is that if you don't produce a molecule of CO2, you don't have to capture it. So which means that we need to do all that is possible to find ways in which we can be less reliant on fossil fuels. But on the other hand, from what I've shown also from the multivariate studies, it appears that greenhouse gas emissions cannot be completely eliminated just by moving to other forms of energy sources, and hence carbon capture, utilization, and storage seems to be a critical aspect in this a big maze of technologies that we need to explore. There are barriers to large-scale CCUS. I've explained to you so that we understand both sides of this. And as one of the questions asked, CCUS costs are currently high, but I think we need to pursue efforts to reduce the cost and to deploy them at the right time. What I would also like to mention here for participants who are from around the world is that Alberta is a world leader in CCS. I believe we have the potential to be a role model and to be a leader in this technology. Negative emission technology is very often considered as some kind of a voodoo magic, are important in the long-term goals if we need to go to net zero emissions. I think this is important that we start looking at and studying them in order to understand what their potential is and where they would fit into our climate mitigation pathways. And finally, work at the university, supported by the Future Energy Systems, is working towards some of the goals that I have discussed today. So with that, I would thank you for staying with me for this long, and I'm happy to take questions.
I'm sure everyone at home is clapping wildly, but seeing as you can't hear them, I will clap.
Thank you.
A couple more questions we got. Do you have recommendations for the most relevant ways to report and absorb adsorbent's CO2 separation ability? Are there target metrics to compare with respect to a material's isotherm, heat of absorption, or breakthrough curve characteristics?
Okay, this is a question that I think I would be very happy to answer. So if the person is still around, send me an email to this email address, and I'll be very, very happy to have this discussion. The simple answer is yes, and they are not exactly the kind of metrics that you had anticipated.
And I have a person who asked that email. I have their email address, so I'll make sure it gets to you.
Sure, thank you.
Another question, how easily can the technology you're working on be adapted to capture other greenhouse gases like methane and nitrous oxides?
Methane is a clear target, for example, from fugitive emissions, also from landfills. And that is a place where we are, in fact, working with one of the world leaders in methane separation. This is Professor Steve Kuznicki, who was until recently a professor at the University of Alberta. And they have materials that have the potential to separate nitrogen from methane. And that is an aspect where it has been commercialized. Landfill separation, biogas separation is something where adsorption is commercialized, and there is a huge potential for using adsorption in those areas.
All right, are there any other questions on the from the audience? We have many people saying thank you and very nice presentation, very nice talk. Thank you so much for the talk. But if anyone has any other questions, you have a minute or two more to pop them in.
Yeah, and I'm also happy to answer questions if they would like to connect by email. And I'm very happy to do that.
Wonderful. Also check out Future Energy Systems website. We have articles that are published every month. We have learning resources for kids, for adults, and we hope that you can join us for our next talk. So our next talk is on September 30th at 7 p.m. It'll be another live Zoom event. And we will be talking about the best of both worlds, how bacteria can reduce greenhouse gas emissions and lead to more sustainable energy. And we will be doing these talks once a month. So we hope that you can join us. This talk will be posted on the Future Energy Systems YouTube page, either tomorrow or in the next few days. Give me some time to edit, but it will be on the Future Energy Systems YouTube. So please subscribe so you don't miss any of our exciting content. And thank you all again for joining us. And a huge thank you to Professor Rajendran for his wonderful talk. Anything from the library?
And thank you to the library for hosting this.
Yes, just wanted to say thank you. I know I learned a lot. As Valerie mentioned, we're going to be doing more of these talks. Really excited about. I will be sending out, once that the recording of this talk is up, I'll send it out to everyone who registered just so you have it. And I'm also going to be sending out a feedback link. So if you have a few minutes and just want to give us some more formalized feedback, that would be very handy for us to help sort of craft what our online content looks like going forward.
Excellent. I'm happy to stay for another few minutes to see if someone has a question. If not, I would say thank you.
Thank you so much for watching Future Energy Systems video. Make sure to subscribe so you don't miss any of our exciting content. Check out the links below to our website and learning page where you can find activities, learning extension, and more. You can also sign up on the website for notifications for future videos and interactive opportunities. There's so much to learn as we explore our energy future.